All right, so thanks for joining us today. I hope you all had a great week. Today we have the pleasure to host Parisa, who is an assistant prof at Michigan State University, and she's going to share with us some thoughts on compositional reasoning for natural language comprehension and grounding. So before handing the mic to you, Parisa, let me remind you all of some house rules. As usual, clarification questions will be allowed to be asked during the talk. For people in person, just raise your hand and I'll give you the mic to ask your question so that people online can hear you. And for people online, you just have to type the word question or I have a question. And when the time is right, I'll let you directly ask it. There'll also be some additional time at the end of the talk for people to ask for the question, make some comments, or have a more informal discussion with Parisa. That's pretty much it for me. So whenever you're ready, Parisa, floor is yours.
Thank you very much. So it's 45 minutes to 50, right?
Yeah.
Okay. Thank you very much for having me here. It's my great pleasure, and I'm going to share a bit of our research that we're doing in MSU with my research team. The title is Compositional Reasoning for Natural Language Comprehension and Grounding, Leveraging Neuro-Symbolic AI. So let me start with an example of the challenges that vision and language models, deep models can have right now. Actually, this example is quite old. So this is from 2019. It's a data set called GQA. I think many people are familiar with this problem setting that you have an image, you have a question, and you need to answer the question. Here, the question is the red bike to the right or to the left of the Asian people? And the annotation says right, so it is controversial. Now it's on the right of the image. And then the SOTA model at that time developed, also customized for this task in 2019, also says right, which is correct. Now, this is great because this looks like a complex problem, right? Asian people, then left, red bike, which is hard to recognize, but the model is doing great. So let's ask the second question. So is the red bike to the left of the Asian people? It seems a simpler question with the same semantics. It's yes, no. So it might be simpler to answer by the models, but actually the answers are not consistent. Here, the model says yes, which is wrong compared to the ground truth. So now this is makes us to doubt, like, do these models understand objects, attributes, their compositional and relations, like spatial relations and composition of attributes and objects and so on? You might say this is old times. Many ideas nowadays, like, are including like increase the data, like augment the examples. All the variations of this example with paraphrasing and everything can be put on the data set, and then the model for sure will be able to answer all these questions correctly with the much larger models. Okay. So this is another, now newer. Okay, this is like 5 years later. This is April 2023, and this is DALL-E. I asked DALL-E to visualize this sentence for me: a woman with an apple in her left hand, standing to the right of a car. And you see that, okay, the location of the woman and a car is kind of random. The objects are perfect, right? But the relationships, the apple is always wrong. It's always in the right hand. And this model is 12 billion parameters, right? So it's a huge model, but it still has a problem to answer this. You might say this is still old, right? This is like 6 months ago or more. Yeah, now 1 year. But I'm sure if you give this question to DALL-E, now it does it correctly. What is the point? Can we feed all possible problems and all possible solutions to these models? That is the question, right? Isn't the world dynamic? Human can learn compositionally and generalize. They are not required to see all the possible problems and solutions to be able to answer these situations. So that is why I think like deep learning models still suffer from lack of generalizability in basic reasoning skills. Lack of interpretability is a different aspect, right? I don't know why they answered the first question correct and the second wrong. Why the apple is in the right hand hand? Is that because more right-handed people were observed? Is that the frame of reference that we don't know? Is that the right of the woman or right of the image? And then we know that they all need huge amounts of data to be able to perform. So this is problematic in many applications of natural language processing and computer vision, that actually we think that they are really doing successful in these domains, but it seems that they are not really totally reliable still. So now with this challenge, I want to point to some contributions and research directions that we're taking in my group. Some of our efforts have been joining the community for all these evaluation efforts, right? Many people now working on this, try to create newer benchmarks, more challenging, to have a deeper evaluation of the abilities of these models. That is also, we did some effort in this direction. I also had the idea of integration of explicit reasoning in neural architectures that I will talk about. Also, we have been interested in developing tools and softwares that enable us to integrate this explicit reasoning with neural modeling to make them more reliable. We have some research direction on grounding language into visual modalities and spatial understanding in more complex environments that include both language and vision understanding. We have been also working on a variety of applications that all deal with these basic challenges, like different kinds of question answering, common sense question answering, visual question answering, probabilistic question answering, and so on. So let me start and first explain our research that we did on evaluation and integration of explicit spatial reasoning. As was mentioned, please feel to interrupt me if you have any questions. So these are some efforts that we did. We realized that large language models, especially that at that time we were looking at encoder-based, smaller generation of language models like BERT and Roberta, XLNet, and those kinds. And then we realized that, okay, there is no really benchmark to evaluate their ability for spatial reasoning and complex nesting, multi-hop reasoning in the spatial context. So that's why we did some efforts to create synthesized data, like these environments that you have really block-walled, and you have explanation, like we have 3 blocks, A, B, and C, and A is to the left of B, and so on. We also created some, not only, we could generate this data automatically and synthesize it, but also we gave human to explain the same toy environment, try to see if there is a difference. And then we also created some, curated some realistic data, because this data set that has realistic images with natural language explanation is something that I worked on during my PhD time. We were working at information extraction at that time and try to annotate the spatial information and spatial relations. Now we try to curate this data set to look at it as question answering data set, because nowadays I think it's more common practice that when we want to talk about can models do reason, we evaluate them with question answering. So that means they are able to understand when they are able to answer all kinds of questions. So that's why we also curated this realistic benchmark. Just to explain the process a bit and the type of the data that we generated, this is also related to my older work on formalizing spatial information. We had a qualitative representation with formal spatial representations like front, tangential and proper part, overlapping. So there is region connection calculus and directional calculus. So we tried to map the structure representation of these toy images, like block wall images, and then have this qualitative representation of A has overlap with B, or A is front of B, and so on. And then tried to have linguistic templates just to explain natural language templates and generate explanations of this kind that we call it as story and questions. So we have 3 blocks, A, B, C. Block B is to the right of block C, and so on. And then we have the questions like which block has a medium thing that is below a black square. So the questions are a bit complex and need multi-hops of reasoning. So the result of this work is published. I just briefly point to this. I wanted to introduce this resource. So also we have, this is how our realistic data looks like a gray car is parking in front of a gray house with brown windows, frames, and plants on the balcony. And then the question is, are the plants in front of the car, or the plants in the house? And this was curated based on the previous annotations on a spatial concept, like what is a trajectory that I'm explaining, what is the landmark, what types of relationship holds between these objects, and so on. And we created these kind of questions accordingly. This is the statistics of the data. Of course, this synthetic data could be as large as we wanted, and the variety of configuration could be made, but the human data is rather small, but this was a good platform for evaluation. This is the two variations of find relation and yes-no question statistics. So just briefly point to empirical results that we had for this. We realized, okay, fine-tuning with synthesized data improves the evaluation on different domains. So that was interesting to see. And then we also see that when we fine-tune the BERT, Roberta, that kind of models, with these complex synthesized instructions, it seems that they get better in doing multi-hop complex reasoning. Another result that we had was like when we fine-tune with synthetic data, we can do better on the realistic domain as well. So again, the details of the experiments are in these two papers that you can see. So the data sets that we're having is Spart QA, and the extension is Spartan. If you're interested, you can take a look and the reported results on this. So that was on the creating this evaluation resource, but my interest was to see if we can integrate spatial logic for solving this problem, and try to really integrate this logic in the training process of these models, because the previous practice was really just fine-tuning and transfer learning. So let me explain an example. So how this logic, what idea we had to integrate this kind of logic. Here is the context. The white rectangle is on an orange rectangle. I just use this image to visualize. This is all text-based, so we don't have access to the image. There is also the red rectangle, which is above the white rectangle, right? And then now the question is that, is the orange object below the red rectangle? So this relation is the question. So the initial facts that we have from the text, since this is, again, synthetic, we can have the triplets of the relations easily, and even show them in predicate logic, predicate argument representation, like the red rectangle, white rectangle, the above is the relationship, or the white rectangle, orange rectangle, the above is the relationship, and the query is that below red rectangle and orange rectangle, is that correct or not? So we just have this triplet or predicate argument. You can represent it either way, a representation. We also developed a simple spatial logic here that says, okay, for example, if something A is to the right of B, B is to the left of A. Or if A is near to C, C is near to A. Transitivity, if X is above B, B is above C, then X is above C. So some, and also combination of transitivity of the directions and topological relationship. So we have, let's say, a handful of rules like this. We call it our spatial logic. And now, here is the way that we want to really create the knowledge that we can integrate in our models. So we go for the specific example that we had, the formal representation, white above orange, red above orange. We call this Q1 and Q2. Now, if I apply this converse rule, it says that if white is above orange, then orange is below white. And if it says here, if red is above white, then white will be below red. Then if I have these two things, I can apply transitivity and say now orange is below red, right? So the answer is yes. So now this is the kind of resolution tree or the chain of reasoning that we have here. And now from this, we can generate some logical constraints that says if Q1 is correct, Q3 should be correct. If Q2 is correct, Q4 should be correct. And if these two are correct, then the target should be correct as well. So we don't use the actual resolution or reasoning. We try to generate constraints that try to impose consistency for each step of inference that we're doing for making the conclusion. Now, how we are going to train the model with these rules? We want the model to be consistent with these rules. So one thing that I need to point also is that this is only the training time. So of course, I don't have access to these formal representations at the test time. So I just have natural language text and natural language question, and I have to answer. But we could exploit these annotations during the training time and see if this is transferring on the realistic domain. So that is a side note to pay attention to. But now that the loss that we're having is also something that has been used in different contexts. So we have the task loss, that I want the answer to the question to be similar to the ground truth. So I have a cross entropy loss here for the correctness of the answer. And then I have this constraint loss. And the constraints are logical. So we have a surrogate, like differentiable soft version of this logic added as a part of our loss. And these lambdas actually are learned. These are kind of Lagrangian multipliers, because we have a dual formulation of this loss subject to these constraints, and then we can combine. And this parameter is also trained during optimizing during the training time. So this is basically what we do. Simply the final model, you might say, okay, this is still neural model, but at this we have a distance supervision that tries to make this neural model to be consistent with the spatial logic. So these are part of the results. We have more detailed results actually now for this work, and this is under review. So we tried to add these rules for fine-tuning BERT, for fine-tuning T5, and also we compared it with zero shot or chain of thought and just inference time for the very large language models. So we see that we have an improvement, overall improvement of the results. Let me explain what I mean by K1, K2. So we divided the data set to the questions that needed 1 hop of reasoning, 2 hops of reasoning. And this null actually is the class that we couldn't really explicitly count how many steps of reasoning are needed. Most of them needed kind of common sense reasoning, especially this result rescue is the realistic images that I showed you with the statue on the hill. So we see that there are improvements. Of course, still very large language models are better than fine-tuning Roberta with the rules, but fine-tuning with the rules improves the performance a bit. So here is like cases that actually the ChatGPT did this wrong. This is also kind of a year ago, maybe now it answered this correctly, but when we said a gray car parking in front of the gray house with window frame and plants on the balcony, then ChatGPT says the plant in front of the car, it says no, the answer is no, but the plant in the house, it says actually no, while the answer should be yes. So actually the ChatGPT says I don't know because the relation is not in the text, but we say, okay, just give me an answer, then we push it and it says no. So this was an interesting result still, while we cannot beat the large models. But here, this was interesting. This is a different evaluation data set. It's called a step game. This was developed outside our group in parallel actually with our work. And it was interesting because they had systematically generated questions with hops of reasoning from 1 to 10. So this was interesting that we could test on like even more complex steps of reasoning. And now here we see an obvious improvement that the smaller model like BERT, we trained with this spatial logic, is doing much better than GPT-3, even GPT-3 with chain of thought. So this was interesting that when we had complex reasoning, this result of GPT is really dramatically goes down, and then we see it's even slower than BERT. So yeah, this is the result that we had. We developed models that learn to obey spatial logic during training. And then this logic-based training helped complex multi-hop reasoning. So actually, GPT also one finding that I don't have it on the slide was that the realistic data set included a lot of common sense questions, not really multiple hops of reasoning, but common sense information. And it seems that GPT is very good as at solving the question that needed common sense rather than multi-hops of reasoning. So that is another reason that we saw the improvement on the multi-hop was lower with GPT compared to the realistic question answering data set. What we do right now, we're looking at a variety of downstream tasks that need a spatial understanding. Especially, we look at diffusion models and image generation. We focus on actually a frame of reference recently. We want to try to evaluate this, but this is ongoing and work in progress. So another piece of work that I wanted to explain is evaluation of the integration of explicit knowledge, again, the same type of techniques and approach, but in a different context for probabilistic reasoning with large language models. Let me explain what do I mean by probabilistic reasoning. I don't know if people are familiar with this data on the left. This is some data set that is developed in AI2. It's called Rule Taker. The text is like that. David is big. If someone is big, then they are green. If someone is green, then they are round. So these are not common sense or anything like that. So the model, if you want to ask David is round, the model really needs to understand the context that we're giving to it. It cannot use its own internal knowledge to answer this question. So this was just for evaluation of logical reasoning, quite old work actually. But then we try to make a probabilistic version of this data set. Like David is big, usually we have these adverbs of uncertainty. Usually if someone is big, they are green. Normally if someone is green, then they are round. And there were like previous work that they tried to assign probability values to these adverbs of uncertainty. Like, for example, usually is 90%, normally is 80%, and so on. So we could just combine the probabilities, and now David is round with a probability of 72% will be ground truth for this question. What is the motivation of this? We realize that especially in the scientific domain, like medical domain, there is a lot of uncertain evidences that you want to combine, and you want to see what is the probability of having this disease, if there is a probability of this and that. So we really have questions that need some uncertainty measure when we want the answer, and the evidences and the rules also are uncertain. So with that motivation, we created this data set, and now we have, we start from Rule Taker, and we created Rule Taker Pro. Then we have David is big, Erin is sad, usually, normally, and so on. And then we have the ground truth. But then now, since we generated these probabilities for all the facts and rules, now we also can compute the probability based on some probabilistic inference, underlying probabilistic inference. All this data is, again, synthetic. So we can compute the probabilities. And then we can also create same fashion as the spatial logic. Now we can create these rules that we say, okay, the probability, if these rules are combined, we assume they are independent, then the probability of combination should be the AND of the two facts. So we can simply multiply the probability of the two premises to get the probability of the conclusion, okay? So here is what we are doing. Also to point that there was also a data set before us called RuleBERT that they tried the very first effort to create this probabilistic question answering. But the problem with this is that the questions can be answered with common sense, because the question is that if someone is the spouse of someone, what is the, like A is the spouse of B, what is the probability of B being a spouse of A? So this could be trained from the data because it's consistent over all the examples in the data set. But here, David is big and big people are green in one example. In another example, we say David is I don't know, blue, and blue people are not are green. So it's basically, we push the model. If you want to be correct, you have to really understand the rule that I'm giving to you to this example, and this cannot be captured from the training data. It's example specific. So the constraints that we create, as I mentioned, is kind of, okay, probability of fact 1 multiplied by 90% becomes probability of fact 3, and so on. So we really compute these probabilities, and then we use them as the consistency rules in this context. So the same idea, we have the task loss. Now this task loss could be both cross entropy. If we quantize this, we can also do regression loss if we want to really have the probability generated by the model. But also we want the violation again from this probabilistic constraint, that multiplication of the probability of A and B should be equal to probability of C. So with the same approach, we can train the models. So this, again, we had some results here. We trained the pre-trained language models of the encoder-based, again, generation of the models. And we could also see if we train the models with this synthesized data, we can transfer and do better probabilistic reasoning in other domains. Here are some of the results. We used Roberta here, and Roberta plus PCT is our techniques, like probabilistic constraint-based training. When we added PCT to Roberta, the darker the better. You see that here we have D1 to D5. This is the depth of reasoning, 1 to 5. And then here, M1 to M3 also is the depth of reasoning of the models. This is the data, this is the models. And now we see when we do PCT, when you go forward and you have more complex problems or like multi-hops of computations for inferring the probability of the answer, we see that the result becomes better and more coherently improving here with the PCT technique. So this was interesting. And then we also had some experiments, not integration of the rules in the training time, but also we wanted to do some experiments with just using the large language models and prompt engineering for probabilistic reasoning. But we took some more sophisticated path than just doing chain of thought and those prompting techniques, in the sense that we have the chain of thought, we have just asked the question simply, zero shot, but also we try to map the text to some formal logic, probabilistic logical representation, and then give it to some engine, a solver, to give me the probability of the answer. And here the logical engine that we use is called Problog. I don't know if you're familiar with that. It's a probabilistic version of Prolog, and we have facts and rules, and they are basically, we have the probabilities assigned to them. And then we can have queries. This query says, what is the probability of being green and pink, for example. So we realized that this mapping to code is always effective. And especially with GPT-4 here, it was really good at mapping to this like correct code, that it was not syntactically wrong. So this was very effective to solve the problems when we did mapping to Problog and gave it to the solvers. So basically, we integrated this symbolic knowledge in two different ways. One was just make consistency rules and use that during the training, and then mapping to like solvers, that symbolic solvers, and then try to give them the problem to solve was much more effective than any other approach that we took. So now I'm going to go to the third item that, yeah, question. Sure.
Are there any architectures or open models that you think are more appropriate to add these constraints to, or you think that it will work for any one model and you just find the one that is performing the best to add these constraints?
So you mean that's the application domain? Is that what?
Well, yeah, for example, the last part, when you were adding the constraints for the training or fine tuning, then how do you choose which model to use? Or you like BERT, Roberta, GPT, or any other one that?
Okay. So, I mean, I think consistently we got improvement over whatever base that we use. When we added these constraints, we got a bit of improvement. So, I mean, I cannot say which one is really we have to take, but we didn't apply this on the very large models. If you applied on the very large models, this could be even more effective. But at least with the encoder-based ones, it showed improvement. Yeah, we didn't do this with T5 or even like the like GPT. Of course, we don't tune, but even with T5, we missed the experiments for this one. Maybe the larger model will be better. Yes.
So with GPT type of models, we can't fine tune. But do you think if we use these synthetic examples to, let's say, do prompting, would that induce, like actually improve the reasoning of the model, not just for the same task, of course that will, but like more fundamental reasoning, as in like if we test that prompted model on other benchmarks, now we'll see that suddenly this is a much better model.
I mean, I have seen some efforts that they do variations of the integration of the rules, and then, okay, if I integrate this kind of logic, then the model is able to follow this logic and so on. In our experiments with the spatial reasoning, not this one, actually we tried to add the text in the prompting, the text of the rule. We tried to add the formal representation of the rule on the prompting. It was really not as effective in our case. So that's why, I mean, with the probabilistic reasoning also, they really didn't perform well, but mapping to the solver was the best solution that we got for this. So we really use the capability of the language model to capture the structure, syntax of the rules, and it seems most of the time they are also semantically correct, the code that they generate. So it's much more reliable to really use external solver for this case. Did I answer your question? Yeah. So now this is less neuro-symbolic, but grounding language in visual perception and navigation. I see many people also working on vision and language, so I wanted also to show some of the works that we did in this direction. And so this is some publication that we are having. This is the problem setting that might be some people familiar with this problem setting here. We have an agent that receives natural language instructions, and it also receives visual information from the environment. This is a simulated environment, but the images are photorealistic. And hopefully this is kind of deal with some challenges of the actual embodied AI, but the challenges that we focus is mostly on the language and vision side, right? So this is panoramic view that the agent receives, and the agent needs to select a view that is appropriate based on the instruction at each timestamp. And then it generates a sequence, a trajectory of these views. And the success is if the agent gets close to the target after like following this trajectory. And close to the target is less than 3 meters and so on. So we have the navigation error, success rate, and so on. So this is the problem setting that we are having. Now, as I mentioned, we have a lot of work done on this already published. But some of the challenges that we looked at was kind of, okay, there are sometimes ambiguity in the instructions. Like, for example, the agent, receives the object names that never saw them before or never heard about them or didn't have enough training for them. Like, reach the entrance between kitchen and living room. This is the instruction. And then the image is this. So this is actually, maybe for human, it's so hard to see where is the kitchen, where is the living room, right? But actually, we expect the model to see this is a dining table, these are sofa, so the kitchen is on the right side and the living room is on the left side. But why not just say, reach the entrance between sofa and chairs, right? So that will be much easier. So we try to say, okay, if there are unrecognizable landmarks, maybe we have to translate it to something that is more according to the sensory kind of knowledge of the model. Use the object names that actually the model is familiar with them and give the instruction with that. That is one challenge that we thought could be improved here to see what the model understands and then give instruction in that sense. Another is that sometimes the instruction is ambiguous. You say, go to the door, and all the views include a door. So we should really rephrase and give it some instruction that is more specific. And then there is less ambiguity for selecting. So I don't go to the details of this work that much, just explaining the idea. Here we have the notion of translator. The translator is simply just LSTM because everything else is with a transformer-based backbone, vision encoder, text encoder. So we didn't want to add a more computational complexity for the translator. We just use sequence to sequence and LSTM. But this is plugged in the whole vision and language navigation backbone with a recurrency that is also built on top of previous models for this problem setting. So we have the translator, and the translator is trained to actually rephrase the expression in terms of the objects that are more recognizable and instructions that are less ambiguous. So how we can do this, actually, the key is synthesizing the data again. So when I have the environment, I give it to, I call it the sensor, visual sensory. This is CLIP here. So CLIP is largely pre-trained and can give me all the objects with the probability that are observed in this scene. Like CLIP says, there is a hallway, door frame, room, and so on. And now I say, okay, now I generate instructions that actually include the instructions that CLIP recognizes, the object that CLIP recognizes, because I'm going to use this sensor, right? So I'm going to give an instruction that includes hallway, and that is my best instruction. And then I can use bed frame as well. Bed frame is correct, but maybe it's since it is not in the actual target view, it's too easy, but we have easy negatives. And then we have room that also applies to the view, but it's a hard negative because it's kind of room included in other views as well. So we try to do some contrastive loss with hard negatives and easy negatives and the positive instruction, and then train the model in a way that to prefer this instruction, the translator component actually, to prefer this instruction compared to the other ones. So yeah, this is what we pre-train the model, and then we have this translator training with this synthesized data. You get the environment and generates the right instruction. And this translator, as I showed you, will be plugged in as a component in the whole navigation architecture, and actually receives the original environment and generates the new instruction for us. So the key component that here actually shows improvement on the, like a lot of improvement. I mean, I say a lot of because it's very hard to really improve 1% on this data set. So we got several improvements in multiple data sets. And I think one key point of this improvement is that our model learns the association between like the unknown object and the objects that it knows. And then the translator that is pre-trained tries to rephrase this based on the known objects, and it helps to really deal with unknown, unseen environment when it's placed into action. We have different experiments on different data sets. You see here also we have navigation error decreased, success rate increased. These are also parameters that also depend on the actual trajectory that is followed. So those are really depending only on the path as well, not only the target. So we improve on those all metrics. So one thing that I also follow-up work, that was published ACL last year, but this one is EACL this year. But it's a follow-up of that for the translator that we are having. I wanted to check the time, so we have the time still. One thing that we wanted to focus on is like, okay, we have instructions that are ambiguous. We have maybe we have to push the agent to explain the environment that they're seeing. So for example, if I say go to the door and there are multiple doors in the environment, just tell me that there are multiple doors. Then if you decide for this specific target, I see that you are struggling and I see that, okay, this decision might not be reliable. So we push the model to generate explanation of the environment in the details. And then with that explanation generation, there is one aspect of, okay, explainability, and we can interpret the decisions. But also we realized that we didn't expect that in the beginning, but we realized that actually when we want to generate explanation and we push the model to compare one view to another and say, okay, I have room in everywhere. So then it really improves the visual ability of the model. The model will be more precise and accurate, and the whole overall performance also improved. How we do this again, we can synthesize data. We have 3 categories of templates. First of all, we wanted the agent to say the instruction is complex. We want the agent to say which part of the instruction I'm going to execute now, like turn around and go straight, walk towards the wall and stop. And now the agent should tell me walk towards the wall is the instruction that I'm executing now. And then it says, but I can see wall in all candidate viewpoints. So it can say the ambiguity. And then it explains the target in detail. However, I'm choosing this target. In the target, there are large windows with wooden blinds, glass table, and so on. And these are specific to view 3. So these are in view 3, but not other views. So the model needs to compare globally do like kind of some analogy between multiple views, and then choose for the best target. So these templates can be generated because the environment is simulated. We can augment the data with these explanations with templates, and then we can use them during the training time. This is the architecture that we're using. Again, the same transformer-based recurrent vision and language model is the backbone. Generates representation that can be used for action decision. Action is basically this view or that view. And then, meanwhile, we use GPT-2, because we can train it, to generate the explanation. So we have the GPT-2 generate explanation, and then, I missed the loss here. So our loss actually is combined the generation loss plus the action loss. So we have two losses now that we optimize. We want to get the explanation that is in the synthesized data. We can also reduce the navigation error, of course. So this was actually something that was also useful. As I mentioned, the explanation is kind of interpretability or explainability that we gain. We also gained performance here. You see that again with the success rate. We improve with the success rate depending on the length. We improved and so on. And this is tested on multiple data sets. So we have done some contributions. If you are interested looking at these papers, some of them I didn't explain, like modulating the spatial information of understanding orientation, understanding landmarks, modulating this in the architecture, dealing with the ambiguity, I pointed to that, and then generating these global explanations to improve both interpretability and performance. Some continuing work that we're doing that is actually, I'm trying, as I said, this is not like it was more designing architectures for this task, but I'm interested to see how we can do neuro-symbolic environments here. We have started working on this. It's kind of navigation, but it's a kind of, again, toy environment. You have a grid, and then you have, say, go zigzaggy to the green box that is in the same column as the red triangle, something like that. And the model needs to do compositional grounding, and then needs to plan and find to the target. So this is something that we have started working. We have some results published in a workshop called GenBench, but also this is work in progress. We try to do some neuro-symbolic modeling to solve this problem. I would be happy to discuss to people if you are interested about this. Now, at the end of my talk, I think I have a few minutes still. I want to point to this dominoes framework that we develop on the side of software development for integration of symbolic reasoning in neural models. So I go back to the motivation. So for solving complex problems, just go to entity relation extraction or navigation or question answering. There are actually a lot of concepts, relationships, and compositional concepts that we expect the models to learn about. It's not a single thing, it's multiple models. So basically now we do everything end to end, but actually we in principle, we should be able to learn these basic primitive building blocks to be able to perform the higher level tasks. Decision depends on all these smaller building blocks, or I call them models, and their interactions, and we need to reason on top of these models. If we learn the basic concept and the rules of reasoning, then we will be able to perform higher level and complex actions more reliably. So that is mainly the challenges that we are having now when we deal with complex problems. And now the idea of this framework that we are developing is to make an integration of this. To explain the framework, I have to go back to this basic prototypical example that I usually use to showcase what we are doing actually here. I'm sure NLP people are familiar with this example. This is called entity mention relation extraction. So the task is like, we have a sentence like Washington covers Seattle for Associated Press. The task is to see which one is person, which one is location, which one is relationship. So if we use basic models, like separate models, let's say person classifier, location classifier, relationship classifier, I will get a probability distribution for each of these. Let's say Washington has a high probability to be location. 92% if I just look at it individually, and then 90% to be a person, and then Associated Press has a higher probability to be organization. So now I see the relationship between these two actually says work for. So Washington works for Associated Press. If I decide location for Washington, this is weird because I have these rules here. It says people can kill people, but people cannot work for people. People work for organizations, right? So that's why we want the type consistency here. If I go with just most probable answer for each individual model, I don't get a type consistency. So I'm going to change my decisions and say, okay, now I'm going to, like this is the invalid solution, but now I'm going to decide Washington is people. It's less probable, but in total, I have the most probable global solution subject to these constraints, right? So that is why actually what we want to do. In this framework, we have like learners that are whatever. Here it could be BERT, give me a softmax. It could be just MLP, simple MLP, whatever learning model that you have underlying. Then we get the probabilities, and then we formulate the constraints, and then we try to find a best global solution. So the current, the PyTorch actually is the backbone of the framework that we're developing. It's called dominoes. We have a symbolic representation of the domain with the logical constraints that, for example, type consistency. We have a first order logical representation of the constraints, and then we name these concepts, we connect them to the learners that are the neural models, and then we can reason over all these concepts and the logical constraints to get and integrate this knowledge basically to neural modeling. The constraints can be treated as soft and hard. They can be used during the training as well as at inference time. So these are the key components that we are having in this framework. On the algorithmic side, we have our own algorithm called inference mask loss that uses integer linear programming in the loop of decision making. For training and as well as during the inference time for decision making. We also integrated several algorithms from related literature like sampling loss, dual formulation. You can see the citation of these papers, that is the techniques that are developed outside our group, but we integrated this inside dominoes. The advantage of using dominoes is that you can represent your domain in terms of concepts and relationships. You can express the logic, and then you can apply any of these algorithms of your choice. So for each of these algorithms, it has its own customized implementation. But here we make an abstraction, and you don't need to worry about how to implement these algorithms. Just to give you a kind of showcase of how the code looks like we have word is a concept, phrase is a concept, people is a word, organization is a word. We have pairs of words, and then location, here, I don't have a relation, but we have, for example, work for is a pair of words, so, or pair of phrases. So we can basically represent this with concepts and relationships. Our sentence contains words and so on. We can have the logic, if the question is, the answer to the question X is left, the answer to the question Y should be right. So I have if, I have and all kinds of logical expressions that could be supported here. We can also connect the models to learners. I can say, okay, the answer is more is connected to a module learner, which is Roberta here, for example. So this is just a brief explanation of how we declare the program here, how we connect it to the learner, how we express the logic, and then we call it a program. Then we call, okay, train this program. So when I say train this program, this whole graph with constraints are considered at the same time. And there is a demo that you can see here. Given the dominoes framework, we also try to create a benchmark for evaluation of constraints because we had this framework that makes it easy for us to test different tasks. So we try to test integration of constraints with different tasks like entity relation extraction, question answering, natural language inference, even image classification, MNIST arithmetic, Sudoku. So we have different kind of problems that we use constraints at inference as well as training when applicable. To conclude my talk, I just showed you evaluation of reasoning skills of language models, the efforts that we did in our side, and then integration of explicit reasoning in form of constraints during the training, and inference in the case of spatial and probabilistic reasoning. I showed our work a bit on vision and language navigation using modular semantics and generative models in the loop. And I showed you a bit about the tools that and benchmarks that we built for integration of deep learning and logical constraints. With that, I would like to thank my students and postdocs that helped this research to be done. Like this picture, at least 4 people are graduating now, so I hope that to attract more talents to do exciting research in my group. If you're interested, I am looking for PhD students and postdocs for this type of research. Thank you very much for your attention.
All right. Now we have a bit of time for questions.
Thank you for the great talk. I had a question concerning the first part of the talk on the logic and probabilistic logic framework.
Yes.
So how do you sample exactly the questions? So I suppose you're like, you have a problem space or you have like a bunch of, queries. And how do you sample these? And have you tried, for example, sampling this in different ways? If so, does the accuracy go down?
So you mean for creating the data set?
Yes.
So the advantage that we had here was that we used rule taker data set. So we already had the questions and answers in the logical form. So we just populated this with probabilities and gave it to actually Problog to infer the probability of the answer given the probability of the facts and rules. So we just use this engine to give us the sound probabilities, and the actual sentences were already used from rule taker, which is logical. So we just exploited what they did, whatever effort they did.
And so rule taker, because I don't know, maybe you know this paper, there's this paper called On the Paradox of Learning to Reason from Data. And it's like they show that if you sample problems from like the same problem space, so that are like, it's the same algorithm to solve them, but in different ways, you fine tune on one and you test on the other, you see a drop in accuracy. So this is sort of the reason why I was asking this question, is I was wondering, is there like fundamentally, do you see a similar behavior? Have you like maybe tested this?
So actually the test that we have is done in the space of Rule Taker Pro as well as RuleBert, because RuleBert was another data set that built, and it's totally like news domain or Wikipedia domain. It's kind of more natural. And we saw that when we tune with these probabilistic rules, actually we can do better in RuleBert as well, RuleBert dataset as well. So we did some domain transfer, and I think with the number of hubs, we have actually more results recently on this with multiple hubs, also like training on one hub, testing on 2 hubs. So those also kind of out of domain, right? So those tests also show that we can get improvement. Yeah.
Interesting. Thank you.
Yeah. Thank you.
So I was wondering if we could use like visual reasoning to enhance this kind of textual reasoning, because as a human being, like when we're thinking about at least the spatial, we say like something is above something else, or we read some composition of the scene, we try to visualize it first, and that can help us to go from very complex scene and then try to answer questions based on that visual thing that we have. So I was wondering if we could kind of use that visual reasoning with the textual reasoning too.
Yeah, that is a great question, and I don't know why we haven't done this. I think this is a great idea, because this is the way, as you mentioned, this is the way a human does. You just visualize, and then you really don't need to go to those complex logic and apply 10 transitivity relations to get to, okay, this is to the left of that. You can just see with the geometry of the
exactly.
two. Right. So, but we, first of all, we want to do this pure text-based, and then, I think that is a great idea. It should be done as soon as possible. Yeah.
Thank you.
Oh, yes, thank you. I have a question regarding the probabilistic role thing. I wonder, like, do you provide the model access to like calculators, or otherwise it might have to learn the arithmetic itself?
access to calculators. So you mean when we do inference?
Yes.
What is the question exactly?
With the reasoning over the probabilistic premises, does this mean the language model need to like learn how to do like floating point arithmetics?
Okay, yeah, yeah, exactly. This could be falling in the category of arithmetic reasoning, because we try to push the model to learn the multiplication, though the multiplication is, I mean, the rule of multiplication or the operation that should be used is in the constraints, but actually the model has to do the calculation as well in the loop of training. Yeah, exactly. So it could be looked at as a kind of different type of mathematical reasoning problem. That's true. Yes.
I see. May I have another question? Just one more question. It's really similar to the one before, but like more like on your thoughts on how do we ensure when training on synthetic data, how do we ensure that we're able to generalize beyond the synthetic distribution?
Yeah, I mean, this is something, that phenomena that we observed that was helpful, because I think probably the patterns of reasoning are the same, though the lexical variability is different. But if I have transitivity, probably this is the pattern that is observed in my synthetic data, and the same pattern is in the realistic domain, right? Independent from the actual word that is used. So this is something that was positive indication here, that the model is able to do higher level of abstraction and get just a pattern of reasoning. So actually, this is another good question that I don't know how to do it, is really to evaluate that higher level of, we see the performance, right? That's why I'm arguing this is helpful. But how to really see if what is happening is capturing this higher order, I don't know how to do deeper analysis on that.
Thanks for the talk.
You're welcome.
Hi, thanks for the amazing talk. I have a question about the first part of your talk, where you were talking about, if I understood correctly, you're generating these synthetic examples, and then you fine-tuned existing models with that and showed that this improves reasoning performance of those models on, I guess, both IID and some OOD benchmarks.
Yes.
So we actually have a similar project in the lab, but focused on vision and language models, like clip-like models, for example. And what we are observing is, so we also generated synthetic examples focused on, like, fine-grained understanding about counting, spatial reasoning. Although with such fine-tuning, we are able to improve the performance of those models on similar tasks, like either on the same benchmark or other benchmarks, but all of these focus on fine-grained understanding.
I see.
But we lose performance on general tasks. So let's say if we take clip, we will lose image classification accuracy, right? So, and this we have observed across like multiple projects. This seems to be like a general phenomena, that as you guide these models more towards like improving reasoning, you are losing their foundational capabilities to some extent. So I was wondering if you observed similar behavior in the kind of models you have worked with, and if you have any insights about that.
So that's a good question. I think we didn't do experiment back. Now I fine-tune how it works on a different problem. We just had the scope of question answering. I can say it didn't hurt because, for example, we did Bool QA, that is Boolean question answering, but it's not necessarily a spatial, but it's designed for multi-hop. And for that, it didn't hurt. It actually improved a bit. So, I mean, at least for the question answering with multi-hop reasoning, it seemed the data set that we picked was good. We picked Bool QA because yes/no question, it was designed for yes/no question answering, and the format was similar. So I don't think we hurt at this case, but we didn't do massive experiments on different tasks to see actually the representation is richer now for everything or not. Probably not, but I hope that it doesn't hurt. I think there is no reason to hurt, I think, at least for this case.
Yeah, I guess, I mean, if I understand to some extent why this hurts is probably because, like, it depends on the diversity in the fine-tuning data set. And basically, we are sort of specializing the model too much for like particular kinds of tasks. So it is somewhat expected, but ideally, we don't want to be in this situation.
Yeah, that's right. I mean, this is, certainly this is a phenomenon that we see in many things, but you're right, we didn't test it here like vastly, but I have here, I heard this issue happening certainly for different kind of problems. When you specialize it, you lose the generalizability of the representation. Yeah.
can I ask one more question? About your vision language navigation, VLN work, and you're generating explanations.
Yes.
Can we say that these explanations are faithful to model's actions?
Okay, this is a good question. There is a lot of analysis there that we see actually when there is ambiguity in the explanation, the errors are higher. This was interesting for us to see. So I can say faithful in the sense that it tells me something that is relevant for the action that is taken. And it improves the action accuracy as well, as I said, because the visual ability gets extra supervision now. Yeah, I think it is faithful in some senses that we analyzed. So you can look at the details.
Okay, thank you. Yeah, I just had a question about your part of your talk where you're talking about emulating, reasoning with transformer, and then you said at the end that if you can produce the abstract form and then use a solver, like Prolog, logic solver, then it works better. So, but it means that you assume that you have a set of rules which can be used to.
Oh yes.
Yeah. Okay. And so in most of real life problem, we don't have this set of rules. So can you infer, a set of rules directly from the data, and then just instead of just generating the abstract form and then use a given set of rules?
So to make sure I understand the question, this is in the probabilistic or spatial or both? It applies to both.
In both, yeah.
And then the question is that I have the text, but also I have the rules of reasoning. Now I want to see, and your question is that the rules of reasoning are not given usually, right?
Yeah, it's the thing which is hidden, and when you would like to reveal, the set of rules directly from the data.
Yeah, I think our focus actually was here to see if the model follows the rule. So that rule was a part of the problem, the input to the problem. And then the rule was also very specific to the case. So there is no way that I don't have the rule and I can reason green people are happy, right? So that's why I really had this rule, and I wanted to see if the model can do inference based on this linguistic information in the input. So for our case, I think in general the question is right. If I want to do reasoning, I don't have the rules. That is important. But here, given the rules for the probabilistic side, we wanted to see that. For a spatial reasoning, actually, we don't have the rules in the context for the fine-tuned models. We have the rules during the training time because we use them as a source of supervision. But for the test time, we don't have the rules. So there, for the fine-tuned BERT Roberta, we just, the model captured the obedience to the rules during the training,
yeah,
I guess.
But you assume it's the same rules which apply for the test?
Yes, certainly. I assume that transitivity holds everywhere and symmetry holds everywhere, right?
I had a question about the agent in the rooms that's like moving around the different rooms. You mentioned that when you asked the agent to explain its reasoning, it improved like the accuracy of its actions. How do you know if when you ask the model to explain its reasoning, if the explanation it gives you is actually what it's thinking about doing versus just telling you something, but then it does something else?
I mean, yeah, that's a good question. As I mentioned also, it's relevant to the previous question that we did some analysis how the errors are correlated to the explanations. If there is ambiguity in the landmark in this bunch of questions, is that expressed in the explanation? And for that subset, how is the accuracy? So those kind of analysis we did, and it seemed it was faithful. So when there are difficulties for explaining the environment, then the actions had a bit of more errors. Other than that, it's the performance that improves that we also show, okay, these explanations help. And I think our general intuition also is that, okay, we really push the model to do global comparison and analogy for making a decision. So this, hypothetically, this should be helpful actually for visual understanding.
Thank you.
Just related to this question. So I was thinking that when you ask the agent to explain like you can explain a scene and have lots of details, right? But not all of that detail is necessarily useful for taking a certain action. So your action is basically should be caused by a certain part of that explanation. So that's like a causal relationship between the explanation of the scene and the action. So then, like the point would be like how to generate explanations that really cause the action, and stop having every detail in the scene, and that would be maybe costly to just like explain every single point. Like when I look at this, I say, okay, I go to the front maybe to talk to the lecturer, right? But I can just like explain every single like chair or every single desk. That's not useful, right? So then maybe that would be certain like pre-training session, just having a causal relationship between the explanation and then the action.
Yeah, that's true. I think the explanation that we generated was helping the visual understanding in general, not necessarily helping the action, right. Because we did a lot of redundancies, right? So we improved the representation that actually generated for the action decision making, right? We changed that representation because we got a loss from this explaining everything accurately. But for the action, making the action, yeah, certainly many of those are redundant. And I think since this is a good idea, we can actually try to really add another template that says, okay, explain this. I do this because of that. Mm-hmm. I don't know how difficult is that to do that automatically because we have templates. But if we have a way to generate those kind of explanations, then maybe that is additional explanation that could be added to the rest to say, okay, I did see this and that. By the way, I decided this. And here we just say, I decided this, and I see everything in that target. Right. But I don't connect what I see in the target for the what I saw in the instruction, right? So that connection might be a bit hard to do automatically, but I think that is a good idea. Yeah.
Thank you.
You're welcome.
Thanks for the nice talk. I think it's a compelling program that you're presenting here about kind of combining learning and reasoning. I'm just curious about how committed you are to using the external solver, and it seems like that if these approximate inference perceived large language models were able to sort of do long reasoning chains very effectively, then maybe that becomes less important to have. So are you interested in taking that solver to do exact inference seriously, and where do you think the trade-off is there? Do you need to use that?
Yeah, this is a great question. I think as we get more data, we need less reasoning, actual explicit reasoning, right? That is one aspect that you pointed, I guess, right? So, but I think for every given problem, now we have all this data generated in the world. We have this knowledge or solvers available. I think the best approach is that for solving every problem, I have a paradigm that I can combine, right? Combine the knowledge or the solvers or technology that I have. And then again, depending on the problem, I should see how much I afford to use the solver. Like using the solver, it means at the real-time inference, I have issues because I cannot like respond maybe in milliseconds, right, or microseconds. So I will take more time if my variables are too many. So if I really want to do real-time response, maybe just I need feed-forward forward actions to make a decision and I cannot use the solver. So in that case, depending on the problem, I have to use, can I afford to use the solver here? And I come and get the problem that is formally represented from sensory data, and then the solver can solve this. That is good. If I have like time affordance, computational affordance, I think based on this all parameters for solving every problem, we should have access to the technology that can combine these paradigms. That's why I'm really interested to what I call heterogeneous computations. So I really don't want to do everything with neural modeling because depending on the situation, this is very limiting us, right?
Thank you.
All right, let's thank Parisa again.
Thank you.